Welcome back, everybody. So this week I want to talk about points to analysis. In the previous weeks, we have already talked about the basic general monotone framework and then call graph analysis and how points to analysis can actually aid call graph construction. But there are many other uses of pointer analysis, not just call graph construction. And I think it's important to explain these other uses as well. And while I'm doing that, I will also be explaining other pointer representations that we have not yet discussed so far, because they can really be useful in these other application contexts. So let's directly dive into the topic. So in the previous lecture, I talked about call graphs as they model a program's calling structure at compile time, and that we also want to have a call graph that is sound. And we also discussed that Spark, using its points to analysis algorithms, is a framework that allows you to aid the computation of these call graphs. And then we also talked about the fact that you can compute call graphs and points to sets together on the fly, which can actually enhance precision. Now, we also discussed these different types of pointer analysis. So there's the general Anderson style analysis, which is pretty much Spark's default setting. So this is a standard inclusion-based pointer analysis that tracks all allocation sites separately. Then we have different variants that I also discussed, which you see on the slide. So we discussed RTA, where basically you are just looking for allocation sites in the program in general, and you are disregarding variable assignments. And at Spark, this is modeled by using only a single variable node. Then we discussed the much more precise VTA analysis, which is pretty similar to Anderson style, but it has the main difference that it uses types as allocation nodes, so it's more coarse-grained. You cannot distinguish different allocation nodes of the same type anymore. And we also briefly discussed Stensgaard style analysis, which is an equality-based analysis that Spark basically models by using bidirectional edges in the pointer assignment graph. Today I want to talk about other uses of pointer analysis and how different variants of points to analysis can actually support these uses. And the first distinction that is sensible to make when one talks about pointer analysis in general is that there are different types of pointer analysis, and one is called points to analysis and the other one alias analysis. In the points to analysis, we basically want to compute for each variable the objects that the variable can point to. So we query for a single given variable and we get basically a set of objects. In an alias analysis, we want to determine which variables in the program point to the same objects. So it's a different query, right? So here we query with two variables and we also don't get objects. We just get a binary answer, true or false. That's the general concept, except that this is not quite true because, as we already have learned, for most such interesting problems here, we need to approximate them in static analysis. So also here, we need to do the same, which means that in points to analysis, we actually compute for each variable, not the concrete objects that these variables point to, but actually the allocation sites whose objects the variable may or must point to. Okay, so here the points to set is not actually a set of objects, but it's rather a set of allocation sites. And depending on the analysis, we'll still be talking about this, you get an answer whether, for instance, A1 is an object that this variable definitely must point to or only one that it may point to. Then alias analysis, it determines which variables may or must alias, which means they may or must point to the same objects at runtime. So in particular here we distinguish may alias analysis from must alias analysis. So whether two different variables actually may or must point to the same memory location. So what does this mean? So if such a may alias analysis tells you true, then it doesn't actually mean true for sure. It actually means yes, true, maybe the two variables are alias. So it might be there's one possible program execution along which at some point in time v1 and v2 point to the same object. Likewise, on actually the other way around, if it tells you false, it actually means that this cannot be true. So actually here, if you get false, this gives you a guarantee. It gives you the guarantee that v1 and v2 nowhere during the execution of the program can point to the same object. So they're definitely distinct. With must alias analysis, it's the other way around. So here true is the definite answer. So if you get true, it definitely means that v1 and v2 will point to the same object. And if it tells you false, then this means maybe not. They might point to the same object, but you don't know for sure. So let's take a look at this a bit more deeply. So here's an example I want to show you, right? It's a relatively simple program. We are allocating two objects, an A object and a C object, but the types are not important here. We are assigning them to these variables, and there is a potential assignment of A to B, which potentially causes these two variables to alias. And C and D after that statement are definitely aliased, okay? And now we can actually go through these different queries and see what would be the right answer, right? So let's take a look at may alias A and B. Can A and B ever point to the same object? Well, for sure they can, right? Because there's this possible execution here that actually assigns A to B. So the right answer here is true. But is it also true that A and B must alias? And if you look at this here, well, that's actually not really the case, right? Because there is an execution where you bypass this branch and then they don't alias. So this is false. Excuse me. If we look at may alias A and C, well, that is also definitely false, right? Because they are never assigned to one another. And if we look at must alias C and D, well, that's actually an interesting question, but if you look at it, so D is definitely being assigned C. It's not assigned anything else, so you might come to the conclusion that this is true. That might seem like a sensible answer, okay? But the thing is, that is not quite true because we might be extending this program like you see here, right? So there might be another assignment to D, for instance. And in general, over the lifetime of an entire execution, two variables never always alias with one another, right? That's because over the whole lifetime of the program, at the very beginning, each variable is initialized, at least each pointer variable is initialized with null, right? So at the beginning of its lifetime, it doesn't point to anything, so it certainly doesn't alias anything. So if you ask such a general question, must alias C and D, without telling at which program location you actually are asking this question, that doesn't even make sense. So the only sensible answer to this always has to be false. Because if you look, for instance, at this program location here, just after the object C has been created, C and D definitely don't alias, right? And so that's reason enough to say this general claim that C and D always alias, that doesn't hold. And so conversely, that also means that must alias analysis, it typically always needs to take control flow into account. So if you don't look into control flow, if you are trying to do a flow insensitive must analysis or must alias analysis in particular, that doesn't really make sense. I don't see any way in which that could make sense. So let's take a look at a flow sensitive must analysis or must alias analysis here. So for instance, here what I have now changed is that I've actually added two statements to the query. So this query means, does the value of A just after statement S1 here, actually alias with the value of variable d after statement S2? And that's a valid question, right? That's one that we can ask. And if you take a look at that, then you will see that actually for this particular query, it's definitely false. If we look at this for statement just after statement S3 here, then assuming that this means really after S3, if we write it this way, then this is true, right? Because after S3, we are actually here. So after the statement, we are here. Therefore, because they have just been assigned, A has just been assigned to D, that definitely holds. Must alias B and C at S2? So after the statement here, well, that's actually false, right? Because C has been assigned the C object, but B has not. So now if we look at this last statement here, then let's take a look at that. So we are seeing whether B after S2 aliases with C after S3, okay? So B after S2 is, well, it's potentially pointing to this A object, right? And then C after this state down here, it's definitely pointing to the C object, right? So that means there are distinct objects, and that's why here we actually also get false. So what you can see here is that, and that's actually an important point I want to bring across, these statements, they matter, right? So the distinction in the statement S2 versus S3 here in this query, that does not matter. We both times get the result false, but up here it does matter, right? So all I changed here was that for D, in the one case we're looking just after statement S2, and in the other case after statement S3, and the result actually changes. And so if you now think about a flow insensitive analysis that basically disregards these statements and only looks at the entire program without looking at control flow, well, then it has to decide on a conservative answer, right? And as you can see here, the conservative answer is basically always false, right? So you would basically have to put this into the same equivalence class and this as well, and that always brings you false. And that's why I'm saying a flow insensitive must analysis doesn't really make sense. It's always doomed to give you false as a result. So you will not find that very useful. And the same is generally true, so not just for alias analysis. And that's because really most program properties you can think of, they don't always hold, right? There's always some place in the program where typically that property is violated, often, for instance, at initialization time. And so therefore, really most must analysis have to be flow sensitive. I would even go so far as to say they all have to be. I haven't come across a sensible one where this didn't hold, but maybe there is an exception. This does not hold for may analyses because they only determine whether a property may hold at all, right? Somewhere in the program. And that can certainly always be the case, right? So a may analysis is perfectly fine to compute in a flow insensitive way. Yeah, so that's one important relationship that I want to make clear. And another one is also an important relationship between alias analysis and points to analysis, because one thing that is important to understand, because it's also very often used in practice, is that you can answer such alias queries, alias v1 and v2, through a points to query, like you see here. And this at least holds for flow insensitive may alias queries, like you see here, right? So if we are asking the question, may v1 and v2 ever point to the same object anywhere in the program, then you can compute this as follows. So you compute the points to set of v1, which gives you a set of allocation sites. You compute the same for v2, which gives you another set of allocation sites. You intersect them, right? So this will give you all the allocation sites that both variables have in common in their points to sets. And if that intersection is not empty, right? So if there are such allocation sites, it means yes, these variables, they can point to the same objects, and then these objects, they will be allocated at any of these intersecting allocation sites. Like I said, this works for May alias analysis. For must alias analysis, it would be at least more tricky, because then you would have to have also a flow sensitive points to analysis. There are some that exist by now, and it's actually an area of research that we are also heavily engaged in, but they're not yet very common. So many points to analysis are still flow insensitive. But yeah, because this equation here holds, you can, for instance, use Spark to do alias analysis, right? So in general, you can determine whether two variables may alias by using Spark's points to analysis result. But you have to be a bit careful because if you use, Suits or Spark's implementation of pointer analysis, you should not just be using any points to analysis algorithm if you want to do such an alias analysis afterwards. Why is that the case? For instance, let's say we were to take VTA, okay, and we want to do alias analysis. Then let's take a look at this program, okay? So here we are allocating two distinct strings, two distinct objects, and this variable becomes aliased with this one, and this variable becomes aliased with this one, but there's no aliasing among this block and this block, right? So they are distinct. Now when you go through this program with VTA, you will get this pointer assignment graph that you see here. And now remember, in VTA, what we are propagating through this graph are types, right? So we are basically propagating this type here throughout the graph, which gives us this result in terms of the types. But now the interesting thing is how Spark actually implements this, because Spark, in order to represent this type, it will non-deterministically choose any of these string allocation sites. Could be any of those two, could also be a totally different string typed allocation site in the program. That's the representative for this type. And then it simply adds these allocation edges that you see here, right? Because there is a string typed allocation site being assigned to S1A right here. And it will also use this arrow here because there's also such an allocation site assigned to S1B. And now it simply determines reachability, right? So it now computes that these two variables here, for instance, they are reachable from the same allocation site. And therefore, also this same allocation site will end up in both points to sets for these two variables, and also for these two variables, of course, right? So we'll end up anywhere. And therefore, then also in particular, the query may alias of S2A and S2B will return true. Although looking at the program, you can clearly see that this is not the case, right? And so the problem is simply that these two allocation sites here, they're not being distinguished anymore. They're just conflated with one another. That's not what you want, right? So the solution is in Spark to actually use its default setting, which is the Anderson style analysis. And that then in particular keeps the allocation sites apart. So here the pointer assignment graph will look like this. And now you will have distinct points to sets, right? So this allocation site becomes a member of the points to set of S2A, and this one a member of the points to set of S2B. And therefore here, may alias of these two variables returns false, which is what you want because it's the more precise result. Okay. That's all I wanted to cover in the first part. In the next part, I want to talk about which is more expressive, points to analysis or alias analysis, and when you would probably want to prefer one over the other.